Hello, and welcome to this presentation for a paper submitted to the Global IoT Summit 2020 conference as part of the second main track on IoT applications, services, and real implementations. My name is Tarek El Saleh, and I will be presenting this work on behalf of our group at the University of Surrey in the UK and our collaborators at Aarhus Municipality in Denmark. The title for this paper is Enabling Context-Aware Search Using Extracted Insights from IoT Data Streams. So I'll quickly go through an outline for this presentation. So I'll start off with an introduction about IoT data streams and search, what the challenges and aims are for this work. I'll then present the system architecture and information model adopted. And then I'll be going through the components of the architecture, namely the data broker, or data exporter, the broker, the stream monitor, pattern extractor, the indexing component. And then I'll be presenting a prototype based on this architecture. And then we'll be finishing off with the conclusion. So in the past few years, we've noticed a rapid increase in deploying IT infrastructure and sensors in urban environments. And this involves reporting information in various areas such as traffic, air quality, weather, public transport, and waste collection. Observation and measurement data emerging from this in open networks is done through open urban data portals. And examples of this we could see are from London and Brussels and in Aarhus. Or they could essentially come from closed networks which are confined within a specific domain or entity. And due to this plethora of data, finding and accessing the data becomes a key challenge. When it comes to search, most IT systems rely on metadata descriptions for searching and discovering data sources. And this is a limited means to search for patterns and change within the IoT data streams. In the open internet world, conventional search engines are designed to process hyperlinks and multimedia data, but not very effective in searching for sensory observations and measurement data. So challenges here would be providing an effective search and discovery mechanism for an IT system, which requires indexing by finding relevant resources based on temporal, spatial, and thematic data. It'll involve analysis of streaming data to find patterns and changes in the raw data. A key challenge associated with extracting patterns or insights is the processing and interpreting of IoT stream data, which involves handling variations in dynamicity and quality. But also, when collecting sensory time series data in IoT deployments, missing values and incomplete observations can be expected. So the aim here would be to build a platform that includes IT sources from different systems and sources, which involves providing indexing, search, and discovery across multiple platforms and systems, to monitor data streams for fault recovery and compensate for missing data, to provide context analysis for data sources, and enable search and discovery information based on historical data and patterns. And then as validation to demonstrate an urban open data ecosystem as a use case. So with regards to the system architecture, the system is designed to enable integration and processing data at an urban scale. It easily scales to support larger data sets through sharded geo-indexing. All communication between system entities use the mainstream HTTP protocol. Data is exported from an open data portal, which employs CCAN as its metadata repository. The exporter semantically annotates based on ontologies that focus on IoT, namely IT stream and SSN and SOSA. This is then represented and exposed as NGSI LD entities. An NGSI is a specification defined by the ETSI group as a standard for defining a meta model for encapsulating domain models. And then the exporter publishes these entities to an NGSI LD broker. We then have components for pattern extraction and indexing, which accesses the data and associates the metadata via the broker. And the pattern extractor analyzes data and generates high-level events that are published back to the broker. This is an illustration of the architecture, and we'll be going through each of the components in the following slides. With regards to the information model, this is an illustration of the concepts that are adopted from the ontologies that make up the information model. So the first component in the pipeline is the data exporter, which is essentially a semantic annotator. And what it does is periodically sends a request to a CCAN data store API to obtain the latest data. If a new sensor is detected, a sensor and IT stream entities are created in the NGSI LD broker. Sensor observations and measurements are stored as stream observations, observation entities in the broker. Observation IDs are also stored and a time to live index, which are used to delete observations from broker after a expiration time, which is useful for limiting the number of entities in the broker. Two properties are required, namely the SOSA observes and the geolocation properties, which respectively are used to capture information about the phenomena and the location. Location or data is represented as a GeoJSON object, and observation and measurement data is mapped to the stream observation entities, and uses data type properties such as result time and has simple result for capturing the timestamp and the values, which is then used by the pattern extractor to construct observation windows used in data analysis in patterns and representations. So with regards to the broker, the broker is the second component of the pipeline, which essentially is an NGSI LD broker, which provides the capability to use repetitive queries to create subscriptions. Detected patterns for data streams are published to the broker as IoT stream events entities by the pattern extractor. Patterns can be queried and users can subscribe to these events. So for example, a user can subscribe to traffic congestion events on a route that he or she is taking and can be notified by emerging events in near real time. So as I mentioned before, data streams can experience faults, such as missing data due to problems with the IT deployment. So we have a component which is the stream monitor, which observes data streams with high quality metrics. For example, metrics to do with consistency and frequency. And then what it does is it fits a model to the data to estimate the probability density probability density of the data, which is based on a kernel density function. It employs Markov chain Monte Carlo methods, which are designed to generate samples from the probability distribution. The Markov chain Monte Carlo method is capable of then generating samples for time slots that fit the data. And then generated samples are used to impute missing values by marginalization over samples for the missing values. And here's an illustration of the process where the stream monitor has a subscriber subcomponent which subscribes to the broker and then is notified with the stream observations from the streams that it is subscribed to, and then applies the data imputation based on whether there is missing data or not from the stream. Here's some graphs that illustrate the steps on how the monitoring is done, and in terms of its performance, it's compared to other methods that are used for data imputation. With regards to the pattern extractor, it uses stream observation to detect high-level events. A machine learning method is used to analyze a group of source observed properties. It subscribes to the broker, which includes spatial, temporal, and data type specifications for data streams. It uses a pattern extractor, which caches observations that are necessary to perform analysis. The pattern extractor constructs a 1-hour window to analyze the data when observations are received from each stream in the group. The result is a label for pattern of data, and this label, together with the start and end times of the pattern, is represented as an IoT stream event, and then is published back to the broker. Broker then makes these patterns searchable. And here's an illustration of the process, where you have the data exporter pushing stream observations to the broker, and the pattern extraction here as a traffic analyzer, subscribing to the stream observations and then creating the events based on a cascade of analytic processes. Essentially, the algorithm that is used involves piecewise aggregation approximation to reduce quantitative data. It applies the Lagrangian multiplier to normalize the data. Performs then a clustering method to group the data to clusters. For example, for traffic density, it'll create clusters for low, medium, high, and critical. And for traffic flow, it'll use clusters that represent congestion, low, medium, and high traffic. So the advantages of this method is that pattern identification and clustering methods is used to analyze trends of data and changes in trends rather than relying on single or multiple observations. And here's an illustration of its performance with regards to other techniques. With regards to the indexing component, it exposes an NGS-ILD query interface. It creates subscriptions from metadata changes at the broker to keep indexes up to date. In terms of indexing, it receives a notification that updates the index appropriately each time the metadata changes. The index itself consists of 3 parts: 2 indices that map entity IDs of IoT stream and source sensor to geopartition key, and also a geopartitioned index containing data. The partition key is computed according to location of data, computed by intersecting sensor locations and JSON objects with predefined regions in the form of countries. It then stores the entities in the index as a graph based with a top level entity being the IoT stream. With regards to the prototype, we demonstrate a use case for urban information search and retrieval with data from the municipality of Aarhus. It demonstrates how higher level abstractions can be used by citizens and urban planners to make informed decisions, for example, traffic patterns. It makes data more accessible to users and allows search for patterns and trends rather than exploring large volumes of data. It can enable transport authorities to use the tool to identify congested roads and to detect correlations between different traffic patterns in different parts of the city. So here's a set of snapshots from the web user interface that the user can access. So on the left side here, you have a search form where you could enter the location, data type, the pattern, and time range. You can specify location area. And the result will be a visualization of the map in the form of a map with a side panel showing all the information about the IoT streams. So to conclude, we presented the search engine for streaming IoT data. The key components of the proposed system discussed to achieve have been discussed. We've achieved interoperability across different systems and platforms by using a common NGS-ILD model description and representation model. We've enabled searching for data sources based on spatial, temporal, and thematic features, and a search function has been developed based on high-level concepts associated with patterns. We applied data segmentation normalization which is used to create patterns by using a clustering method to group the patterns and labels. We've also developed a stream monitoring component to compensate for missing data using implementation, which is expected case for real-world scenarios. And we've developed a prototype which can be accessible via the link below. And to finish off, I'd like to thank you for attending this presentation, and I'm happy to answer any questions.